Smart Elderly Car, a project to improve the mobility of the elderly and disabled population. This project will focus on the research in technologies for the development of an autonomous electric car to assist the elderly in predominantly urban environment. The software architecture is based on the open-source robot operating system. Our navigation proposal is divided into executive control and lower-level reactive control. Executive layer calculates a path consisting of a sequence of lanelets that can be modified depending on the performance behaviors. Experimental platform is an open-source electric car based on a TVEvo chassis developed by the Open Motors company. The chassis has been equipped with a backup batteries, a tubular car body, some sensors like DGPS, LiDAR, stereo camera and odometry, and it has been modified to be autonomous. Of actions and events that take part of a specific behavior are obtained through a priority net, implemented by the RoBraf tool. The goal of the local navigation is keeping the car within the driver lane in a safety way and avoiding ahead obstacles using the pure pursuit and vein curvature methods. Environment perceptions is based on 3D semantic segmentation obtained from our IRF net. The demonstration consists on navigation autonomously the car along a given path defined by lanelets and switching between autonomous and manual mode when the driver touches the steering wheel or the throttle pedal.
Good morning and welcome to the demonstration of the Robesafe group. I would like to present a little bit our group. The Robesafe group at the University of Alcalá is dedicated to the development of perception system applied to the field of service robotics and e-safety. Our group is working in the last years in robust perception system and machine learning techniques applied to the autonomous driving, and 3 years ago we plan to validate our techniques in real environment using a real prototype. There are many companies and research groups around the world that are involved in these tasks, but our group or our approach is different. We bet for a new and growing up trend as is the open source vehicles in a sector dominated by big companies. Our idea is to control the whole implementation stage in an open way, and where we could contribute in a collaborative way to implement standard tools and products. With this background, I would like to present you our H-car concept. For this demo, we have 3 different rounds when we want to demonstrate 3 different behaviors. The first one will be a lane keeping, the second one will be a switching between autonomous and manual mode, and the third one we test our avoidance obstacles system. Now we have our team ready for the first of the behaviors. Now the car is starting for a destination. It is in the starting point, and we are going to perform a trajectory in an automatic way. Then our team is ready, and we are going to start our keeping behavior in the moment that our driver, that is Felipe, wants to start. Boys, we are ready? Okay. Now the car is moving inside the lane. Our system is based in a DGPS that obtain a global localization in a precise way. As you can see, the borders are obtained using a previous roadmap based on lanelet. This technique was presented in the historical route of the Bertha in Germany in 2014. We use this approach using lanelets. Lanelets are segments of lanes in order to know the limits, the borders of the road. Our system is now driving in autonomous way, as we can see, and we show then in the screen our semantic segmentation system. This is the system that we use in order to detect obstacles in the lane. Our system now is driving autonomously and is able to detect obstacles in the lane and stop accordingly. In this first round, we only drive in autonomous way without obstacles in order to demonstrate the robustness of our lane keeping system. Now the car is performing a runabout, and now is approaching to the tribune where people is attending this interesting demo. Our group is very concentrated in this demo. Hi guys, you can shake your hands. You can say hello to the tribune, to the audience. This is the University of Alcalá team, okay? We are approaching to a difficult cure because this cure has many trips and sometimes some of the satellites are hidden, but we hope that we have a good performance in this cure and we can finish this first behavior in a correct way. I would like to highlight that this is the first time that the group has a demonstration, and I hope that all the demonstration will be successful. Okay, well done. Our system has performed the cure in a correct way. I would like to highlight then that the system is driving at a maximum velocity of 10 kilometers per hour because the environment is very cured. But this prototype can drive up to 100 kilometers per hour. In our campus, we check the performance of our system up to 50 kilometers per hour. Now we are approaching to the destination of this first round. And as you can see, all the track has been done in autonomous way. Okay, well done. Now, I would like to say you that this prototype has been developed under a project called Smart Elderly Car. This is a collaborative project developed in the last 3 years, from 2016 to 2018, between the University of Alcalá and the University of Vigo, and has been funded by the Spanish Minister of Science and Innovation with the goal to research in technologies for the development of an autonomous electric car to assist the elderly population in urban environments. Now, our team is preparing the second round. He is launching this new behavior. In this behavior, we are going to check the switching between autonomous and manual mode. I would like to highlight then that this car is handmade, completely handmade. It's based in an open source electric car based in a chassis developed by the company Open Motors. This is an emerging Californian spin-off. But this chassis has been equipped with many other instrumentation in the car, all of them developed by our group. Okay? Our team tell me that everybody is okay. Okay, then we can start the second round. In this case, now we are driving in autonomous mode. We can see the semantic segmentation in the screen when we can see that the road is correctly detected. Okay. In some moment, I'm going to say to the driver, Felipe, that change to manual mode. In this case, he puts his head on the wheel, on the steering wheel, and we transfer the control to manual mode. Felipe, when you want, you can transfer the control, please, when you want. Felipe, you can switch the control, okay? We see that he put his hand on the steering wheel and the car stopped. In order to switch again the control to autonomous mode, the driver has to press a button that is in front of the driver, just in the right part. You can press the button, please, Felipe, and we can continue the driving in autonomous mode. There are different ways for switching between autonomous and manual mode. One option is to put the hands on the steering wheel. Another option is to press the brake. Another option is to press the throttle. Now we are going to check a second option, a second possibility, that is to press the brake. Then when you want, Felipe, you can press the brake in order to check this other way for switching the control. Okay, please press the brake, please. Okay, as we can see now, the car stopped because now it's in manual mode. Now we are going to switch again to autonomous mode, pressing the blue button that is in front of the driver. Okay, well done. Our system now is driving in autonomous mode. And they are approaching the tribune. When we have the audience ready for seeing our prototype, I think that this has been ratified with a big applause for our team when he's crossing the tribune. Okay, now we change again the control to manual mode, in this case pressing the steering wheel. Okay, now the car stopped because now it's in manual mode, and we are going to switch again to autonomous mode, pressing the blue button that is in front of the driver. Okay, well done, team. Our car is working correctly in his behavior. Now he is performing lane keeping behavior in autonomous mode, as you can see in the video. We are approaching the most difficult curve in this track, and I'm sure that our system is going to perform the curve in a correct way. But we have to take into account that in each demo, we know the Murphy law. Nice thing. We are approaching the second destination. I would like to explain you that as all navigation systems, we have three main modules: a planning module, a perception module, and a control module. The planification, our planning, is based in a previous map, based in lanelets, as said before. Our perception system is based in the fusion of LiDAR and cameras, in this case a stereo camera. And then we have a control system that is divided into two levels: an executive control level and a low level reactive control. Our reactive control controls the driver, the car, using lanelets and the position of the vehicle, using a sequence of actions and events that take part of a specific behavior that are obtained using a Petri net implemented in a RoboGrab tool. But our low control is reactive control, and is based in two algorithms: the pure pursuit and the beam curvature method. Okay, now we are approaching for the final round of our team. In this case, this is the most dangerous demonstration, because in this case we are going to demonstrate our obstacles avoidance system. We are going to use in this demonstration real pedestrians and a real obstacle. Okay, the question for our system is: what happened if suddenly obstacles appeared in the lane of the vehicle? Now we have a perception system able to detect obstacles in the line and to avoid these obstacles accordingly. We are going to start this dangerous demonstration, but we are sure that the demonstration is going to be successful, because we are test this demonstration many times and always work perfectly. Now the team is ready. We can start when you want. We start in autonomous way, and a pedestrian cross the lane, the car stops, and then when the pedestrian crosses the lane, the vehicle starts again driving in the correct trajectory. We can see in the segmentation image the detection of the different obstacles of the pedestrian. Now we are ready for a sudden situation, as is a box in the lane that is avoidance by our system. An applause, please. Okay, now we are ready for other pedestrian that is crossing. As you can see in the segmentation, is in red color. We detect it. We detect this pedestrian, and the vehicle stop and return to the planning, the previous planning, in a correct way. Okay, as we seen, this is our system able to do three different behaviors that we have demonstrated today: a lane keeping, a switching between autonomous and manual mode, and obstacles avoidance. With this, we finish this demonstration. But I would like firstly to present our group. We have many persons involved in this demonstration. The first one is Felipe, the driver in this demonstration. An applause for him. The second one is the co-driver. That is Miguel, that has been in charge of the low-level control. An applause for him. The third one is Alvaro, is the expert in DGPS. The fourth one is Eduardo, our expert in semantic segmentation. And then we have another collaborators, and Javier Araluce, the person that has developed our switching system. Rafael Barea, our expert in ROS. Pedro Revenga, our savior, is our MacGyver, because always solve every problem that we have. And finally, the ceremony master is me, and is the coordinator of this group. Thanks a lot to my team, because they have been